Either way, then you also have another other particle that's a completely different kind of boson, which we call gluon. And there's actually 8 different kinds of gluons. Now, to understand what a gluon actually is, just think of glue, and that's why it's called a gluon. Gluons is what holds matter together in the sense of it actually connects the particles of quarks together to make bigger particles. And it's also what holds together the nucleus of the atom. Now, in terms of elementary particles, the gluons that we're talking about here are the ones that mediate the connection between quarks. There are a separate part of type of boson, which is actually a compositive boson, which is when you put different quarks together and you make something called a meson that actually mediates the strong force that holds the nucleus of the atom together. And we'll talk about that in the next video. On this video, I'm talking about the gluons, the elementary strong force, or the fundamental strong force that actually holds together the quarks. Without this force, you wouldn't have anything bigger than a quark. Quarks get together by the action of gluons, and there's 8 different kinds of gluons. And the only difference between gluons is their color. Now, it's not the same thing as you think of color or in terms of electromagnetic color or how much energy in terms of photons this color is actually having or releasing. It's more like something that we call color flavor or quantum color. The best way to understand this is to go back to electromagnetism. You know how in electromagnetism you have a positive charge and a negative charge? In strong interactions, you have different color charges. And it's just what we use to actually explain this strange concept. And it's just kind of like, you know, how I decided to call a door. This is what the scientists did here. They called the behavior of the gluons color charge. And there's 8 different kinds of gluons, and depending on which kind of gluon interacts with matter, it's going to create a different kind of color aspect. Now, gluons give quarks a color charge. Each quark has a specific color charge. They can be either green, blue, or red in terms of color charge. Now, these are not the same colors of the color that you think of when you see things. That's electromagnetism. That's a light that you're actually seeing. It's photons. We're talking about color charge. We're talking about something analogous to that, but in the sense of the strong interaction. And it only happens at the quantum level between quarks. And so one quark will act red, one quark will act green, one quark will act blue. And depending on the way they interact with each other, you actually make the different things. Now, so the way I like to think about this, that it actually makes sense to me, is that the gluons basically give the color to the quarks, and then in turn the quarks actually will attract each other depending on the color relationships that they have between them, and it will complement each other. So quarks are attracted to each other because of the color that the gluons give them. And the gluons are the only ones that have intrinsic color charge. In other words, they are the ones that can give color. Quarks only have that color if the gluons give it to them. And that's why you need the gluons to actually attach the quarks to each other. Now, unlike the electromagnetic force or the weak force, this force does not become weaker over distances. And that's actually a phenomenal concept. It's the idea that it doesn't matter how far apart you actually stretch these quarks apart. The force will be strong, just as strong after a certain period of time. It will max out at that number, and it will not decrease beyond that number. So theoretically, if you were to get these 3, 2, whatever number of quarks are attached to each other and just basically stretch them over and over and more, they would still stay attached to each other just as strongly as they ever were. So that gives you the idea that matter is always attached to itself, even if it splits. I know it's a crazy concept, but that's basically what the strong force is trying to say. And while I can talk in the fundamental force video, that actually means that you can't really ever have quarks by themselves, because you would have to put so much power to actually break the strong force that exists between the quarks that you would actually spend so much energy doing that, that if you broke the strong force, the energy that you spent would actually create a new quark, which would then pair himself up with the other quark that you just finally separated. So quarks will never show up by themselves because of this strength of the strong force. But since the attraction between the color, or the complementary nature between the colors, is actually what attracts them, if you go beyond the actual particle that's created by connecting the quarks, you can't feel the strong force at all. And so the strong force only exists within the actual particle that is created by it. Now, this is a phenomenon that we actually call color confinement. Beyond that particle, it doesn't exist. So you can't feel the strong force between two protons. You only feel the strong force, or the fundamental strong force created by gluons, and within the actual proton. Because these particles are creating attractions between different particles at the quantum level, they're called gauge particles, or particles which create a field of attraction. The study of these gluons, because they give this color property to the matter, it's called chromodynamics. But remember, we're not talking about the same color as the visual color that is created by photons. By the way, you can never actually see a quark or a gluon particle directly. You can only detect them indirectly as they emerge as part of a large hadron, which is basically when you connect those quarks together. However, it is possible to actually visualize something that's called a quark-gluon plasma, which is what happens when matter is compressed beyond imaginable pressure, and we'll talk about that at the end of this quantum mechanics video. Now, there's a different type of strong force, which is called the residual strong force, which is created between protons, or between neutrons, or between protons and neutrons, and that is what we call the residual strong force, and it's mediated by a different particle that we call mesons, and we'll talk about that in the next video. But these are the fundamental particles of matter, which create all the interactions and all the forces that matter does. In the next video, before we actually go into compositive particles, we'll talk about the two theoretical particles which have not yet been discovered, the graviton and Higgs boson. They've been theorized but not yet detected, and if they were, they would complete our picture of the standard model of particle physics. I'll see you guys then.